What if I told you the moon shakes, Mars trembles, and even Venus, shrouded in toxic clouds, might be quietly quaking beneath its volcanic plains? We tend to think of earthquakes as an Earth-only phenomenon, but in reality, our solar system is far from still. The ground can move, crack, and rumble on other worlds, and each planetary tremor carries a story about the hidden forces shaping that planet. This is the Curious Playbook, and today we're venturing beyond our own tectonic backyard to explore moonquakes, Marsquakes, and the elusive, still mysterious Venus quakes. Here's the twist. These quakes don't all behave the same way. The moon rattles in slow, strange rhythms tied to Earth's gravitational pull. Mars quakes in bursts, revealing a restless crust and a surprisingly big liquid core. And Venus? We've never even directly felt its seismic heartbeat, but evidence suggests it could be more geologically alive than we ever imagined. The question is, how do we detect a quake on a world where no one stands to feel it? And what can those faint rumbles tell us about the deep, unseen interiors of alien worlds? Let's start with the moon, the only world beyond Earth where humans have actually placed seismometers by hand. During the Apollo missions, astronauts didn't just plant flags and collect rocks. They also built a network of seismic stations. Apollo 12, 14, and 15 each left behind instruments sensitive enough to pick up the tiniest tremor. Apollo 15, for instance, deployed a geophysical station at Hadley Reel, completing a small but important network. A minimum of 3 stations is needed to pinpoint where a quake originates, and for the first time, we could listen to the moon as a connected system. And it turned out the moon has a whole catalog of quakes. Deep moonquakes originate 700 to 1,100 kilometers beneath the surface, deeper than any quake ever recorded on Earth. These are tidal events, caused not by internal heat or shifting plates, but by the gravitational tug of Earth itself. Imagine the moon as a rigid yet slightly flexible sphere, constantly pulled in and out of shape over the course of a month. Every 27 days, like clockwork, these stresses reach their peak, producing seismic events that repeat in the same zones. At least 10 such deep-seated quake regions have been mapped, each one a kind of permanent stress point in the moon's interior. Then there are shallow moonquakes, which happen just 20 to 30 kilometers below the surface. Their origin is different. They occur because the moon is shrinking. For over 4 billion years, it has been cooling, and as it cools, its volume contracts. The rigid crust responds by cracking and thrusting upward in some places, creating small cliffs called thrust faults. NASA's Lunar Reconnaissance Orbiter has imaged many of these features, suggesting that the process is still happening today. Shallow moonquakes are rare, only about 5 per year, but they can be surprisingly strong, reaching magnitude 5.5. That's enough to cause serious structural damage if it happened on Earth, and on the moon, the shaking can last for 10 minutes or more. That extended shaking is one of the moon's seismic signatures. It has a dry, fractured outer layer that scatters seismic energy, allowing vibrations to linger. Another category is thermal moonquakes. Unlike the deep and shallow varieties, these are driven by the wild swings in temperature between lunar day and night. A patch of moon rock can go from minus 170 degrees Celsius before sunrise to more than 100 degrees in the full glare of the sun. As rocks heat up, they expand. As they cool, they contract. This expansion and contraction can cause the surface material to shift or crack, creating small but distinct seismic signals. The Apollo seismic network recorded thousands of them, often occurring at nearly the same local time each lunar day. These thermal quakes reveal that the moon's surface is still subtly evolving, not from impacts or tectonics, but from the daily rhythm of sunlight and shadow. And finally, there are the sudden, violent tremors caused by meteoroid impacts. With no atmosphere to burn up incoming rocks, the moon takes frequent hits. These impacts send seismic waves rippling across the surface, detectable from hundreds or even thousands of kilometers away. By studying these impact signals, scientists can learn about the structure of the crust and how seismic energy travels through it. From all these observations, a detailed picture of the moon's interior has emerged. Its crust is between 55 and 70 kilometers thick in the Apollo landing regions, possibly composed of two distinct layers. Beneath that lies a mantle that transmits seismic waves efficiently, unlike the heavily fractured outer shell. The moon's seismic life is shaped by its lack of water, its cooling history, and the constant gravitational tug from Earth. A seismic personality unlike any other in the solar system. Now, shift your gaze to Mars, a planet long suspected of having seismic activity, but without proof until recently. That changed in 2018 when NASA's InSight lander touched down on the Elysium Planitia, a vast plain chosen for its relative safety and low wind levels. On board was SEIS, the seismic experiment for interior structure designed to detect the faintest ground movements. Over its 4-year mission, InSight recorded more than 1,300 Marsquakes. Some of these quakes were small and local. Others were global events, with waves strong enough to circle the planet. Many originated from a region called Cerberus Fossae, a set of massive fissures likely formed by volcanic stretching. Images show landslides and boulder shifts in the area, hinting that Mars' interior is still capable of significant movement. Like the Moon, Mars also shrinks as it cools, and its solid, unbroken crust can fracture under stress. These quakes are a reminder that even a seemingly quiet planet can store and release energy. And then there are meteoroid impacts. Mars' thin atmosphere offers little protection, so space rocks frequently reach the surface. InSight's instruments even caught the seismic shock of one particularly large impact in 2021, which was later confirmed by fresh craters seen from orbit. The largest Marsquake detected was a magnitude 4.7 event in May 2022. This single quake released more energy than all previous Marsquakes combined. Its seismic waves lasted about 10 hours, and it was the first event where scientists detected both high and low frequency waves, as well as surface waves that had traveled multiple times around the planet. This gave researchers a unique opportunity to map the planet's internal structure in detail. From InSight's data, we've learned that Mars' crust is thinner than expected, about 40 kilometers thick in some places, with denser, iron-rich layers beneath. The lithosphere extends 500 kilometers deep, and below that, the mantle reaches down to 1,460 kilometers before meeting the core. The core itself is larger than previously believed, with a radius of 1,230 kilometers, and it's liquid. This liquid heart creates a seismic shadow zone where certain waves can't pass, explaining why no quakes have been recorded from the Tharsis volcanic plateau. What makes Mars especially intriguing is the role of impacts in seismic research. Recent studies suggest that impact-generated waves can take a more direct route through the mantle, acting like a seismic highway and offering new ways to probe the planet's deep interior. And then we have Venus, a planet almost the same size as Earth but far less welcoming. We've never directly recorded a Venus quake, but everything we know about its size, composition, and surface features suggests that it should be seismically active. Venus has vast volcanic mountains, massive rift valleys, and signs of relatively recent lava flows. Some scientists estimate it could have tens of thousands of quakes each year, many linked to volcanic activity beneath its thick, oppressive clouds. But detecting them is another matter. Venus's surface temperature is over 450 degrees, and its atmosphere is dense and corrosive. The few Soviet landers that reached the surface in the 1970s and 80s survived only a couple of hours before failing. Even with modern materials, a surface lander would likely last less than a day without active cooling, which adds complexity, mass, and cost. Because of these challenges, scientists are exploring creative methods. One is to float balloons high in the Venusian atmosphere, where temperatures are cooler. These balloons could carry infrasound sensors capable of detecting low-frequency atmospheric waves generated by quakes on the surface. Another approach is orbital, using satellites to monitor air glow, a faint natural light in the upper atmosphere that can be disturbed by seismic waves passing through the dense air below. Both methods could detect quakes of around magnitude 4 or greater. Neither approach is perfect. Atmospheric methods lose certain details about seismic events, especially shear wave information, which is crucial for mapping a planet's structure. The ideal solution might combine long-duration balloons with orbital monitoring, creating a hybrid system that can catch and cross-verify seismic signals. Venus remains the biggest unknown in planetary seismology. Detecting its quakes would not only reveal its internal structure, but also help answer whether its volcanic activity is ongoing today. That, in turn, would reshape our understanding of Earth's twin and its long, extreme history. Across all three worlds, quakes act as probes into hidden layers. On the Moon, they tell of tidal flexing, ancient cooling, and cosmic impacts. On Mars, they reveal a planet more geologically alive than we once thought, with a vast liquid core and a still active crust. On Venus, they remain a silent promise, waiting for the day we finally listen. These planetary rumbles remind us that the solar system is not static. Even worlds that seem frozen or dead from afar may be creaking, shifting, and reshaping themselves beneath the surface. Seismology is our way of eavesdropping on these changes, of hearing the deep-time stories locked inside each planet's shell. If this sparked a question in your mind, or there's a planetary mystery you've always wondered about, let us know below. We're always looking for the next curious story to unravel. And if you enjoyed this journey through the hidden rumbles of other worlds, make sure to like, subscribe, and stay tuned, because the universe has many more whispers for us to hear.